In this lesson, we will continue with the practical code demonstration for reading smart contract. In the previous lesson, we mentioned that Ethereum hosts a multitude of smart contract applications, and ENS is one of them. ENS stands for Ethereum Name Service, which provides a decentralized domain name resolution services on the Ethereum blockchain. You might recall from earlier tutorials that we used the ETH getBalance method to query the wallet balance of Ethereum's founder, Vitalik Buterin. His wallet address is a lengthy hexadecimal string. This is a typical wallet public key address, which can be quite cumbersome to use. Is there a more user-friendly way to work with it? Indeed, you can register it through the ENS smart contracts using an intuitive name like Vitalik.eth, where Vitalik refers to Vitalik Buterin for querying purposes. Domain name registration offered by ENS is a user-friendly solution that replaces complex and hard-to-remember Ethereum addresses with easily memorable domain names. Through ENS, users can associate intricate Ethereum addresses with user-friendly domain names. For instance, an ENS domain name like yourname.eth can be linked to an Ethereum wallet addresses. These second-level domain names are typically short, making them very convenient to remember and use. After registering an ENS domain name, it is necessary to bind a resolver. The resolver acts as an intermediary that maps the ENS domain name to an IP address or other information. In the following code demonstration, we will use the resolver. Our task today is to reverse engineer the encrypted address based on the ENS domain name. The code will be executed using the FMZ platform's debugging tool, which requires configuring the Ethereum mainnet as the testing environment. Therefore, an Ethereum mainnet RPC node needs to be set up. Specifically, our code reads wallet addresses using ENS domain names. Following these steps, Step 1. Use a function named nameHash to compute the hash value of the domain name Vitalik.eth and convert it to hexadecimal format. Step 2. Utilize the ABI of the ENS contract and the ENS contract address to query the public function named resolver. This step retrieves the address of the resolver and stores the result in the variable resolver address. Step 3. Using the ABI of the ENS Public Resolver contract and the previously obtained resolver address, query the public function named ADDR to obtain the address of the Vitalik.eth domain. Store the result in the variable Vitalik address. Step 4. Output the wallet address stored in Vitalik address and conclude the script execution. Please note that we are utilizing two resolvers in this process. The first one is the default resolver within the ENS contract. The ENS contract defines a public function named resolver, which allows querying the address of the default resolver for a registered domain. Through this function, the script determines the address of the default resolver for the ENS domain Vitalik point ETH. The second resolver is the public resolver contract, based on the address obtained from the default resolver. The script interacts with the public resolver contract using the ADDR method to retrieve the actual address associated with the Vitalik ETH domain. So let's take a look at our code. In the first step, we need to perform hashing names processing on the queried Ethereum domain name. Here we are using a custom function called nameHash. The nameHash function begins by checking if the name is an empty string. If so, the function returns a string representation of a hash value consisting of 32 zeros. If the name is not empty, it is split using a dot as a delimiter. The first segment of the split is considered a label, and the function is recursively called with the remaining part of the original domain name. Ultimately, the process arrives at the encode function for hashing. The resulting hash is concatenated with the hash value obtained from the recursive call. This approach ensures that during each recursive call, the currently extracted label is processed into a 32-byte hash value. These hash values are then concatenated with subsequent paths to form the complete 32-byte hash value of the entire domain name. As the recursive calls unwind, the process returns to the initial call, resulting in the complete hash value of the domain name. The encode function mentioned here is an API function within the FMZ platform. It is specifically designed for encoding operations on the FMZ platform, supporting various encoding methods and hash algorithms. This function takes 4 parameters. The first parameter is the name of the target hash function. The second and the third parameters indicate the encoding format of the source data. Raw signifies the original type array, original byte array format, while hex represents the hexadecimal string format. The fourth parameter specifies the data to be involved in the hashing calculation, which can be either a string or a byte array. It is important to note that the last line of the nameHash function invokes this function itself in this way, processing the entire domain name string and converting it into a 32-byte hexadecimal string. ENS domain names are transformed into unique fixed-length identifiers. Different hash values for the same domain name correspond to distinct Ethereum addresses. This characteristic ensures the uniqueness and security of the domain name system. The second step is to pass the domain name of ENS. Here we first calculate the name of ENS node. Here we define a variable ENS node which gets the hash value of the domain name Vitalik ETH by calling the nameHash function, and then prefix 0x in front of it to convert it to hexadecimal format, and finally assign the value to the ENS node variable. Next, we register for ENS contract. The first line of code defines a string variable, ENS resolver, that stores the ABI definition of the ENS resolver contract, which contains the method declarations that the ENS contract interacts with. Here we need to find the contract section. In the Etherscan, according to the ENS address, we scroll down to the ABI here and we copy it. Then fill it in here. In the second line of code, we are going to learn a new invocation method on the FMZ platform, using which we register the ABI. The second parameter is the address of the smart contract, which can be queried through the ENS documentation. And the last parameter is the corresponding smart contract ABI, which is defined above. In the next line of code, the first parameter specifies the type of operation as API. The second parameter is the contract address of the ENS, and the third parameter is resolver, which means that we want to use the resolver method. The last parameter is the initial node, ENS node, and this line of code looks up the resolver contract address, resolver address, for the domain Vitalik ETH using the address of the initial node registered in the previous line of code. The third step is to register for the ENS Public Resolver contract. First, we define the string variable ABI ENS Public Resolver, which stores the ABI definition of the ENS Public Resolver contract. Again, for this ABI, we need to look up the address of public resolver in Etherscan. And we find the contract section, again copy it and fill it in here. Again, we use the ABI to register the ENS Public Resolver smart contract. The second parameter is resolver address, which is the address of the resolver contract obtained above. The last parameter, ABI ENS Public Resolver, gives the resolver address as access to the methods in the public resolver contract. The fourth step is resolve domain address. Let's look at the final resolution of the domain hash. This line of code looks up the address of the given domain from the Ethereum network. In this code segment, the second parameter is the contracted address of the resolver address, and the third parameter is the name of the function to be called ADDR, which is the public resolver. The last parameter is the hash value to be resolved, and the resulting value is the ether address of the Vitalik ETH domain. Finally, we use the log function to export the results to a log message. We can see that our methods converts the ENS domain name into an ether Ethereum encrypt address, and we can click execute. Wait for a moment. And here we can see the log message. So this is an example of how to read a smart contract. And as a final reminder, when code involves wallet operations and Ethereum transactions, it is important to make sure that all security measures are properly verified and guarded against loss of funds or other risks. So that's all for today's lesson. We will see you in the next lesson.